Greetings, detectives. Mrs. McKay here, and we're moving on to learning target clue 4.4, which is all about telling the difference between linear functions and exponential functions, as well as recognizing when something isn't either. So let's go ahead and start by filling in our learning target. Our learning target says, I can determine if a function is linear. Make sure you're writing this in. Exponential. Or neither. Using tables, graphs, and equations. I'm going to put a little comma there. So I can determine if a function is linear, exponential, or neither using tables, graphs, and functions. So let's start by first just taking a look at a review of what a linear function is and what an exponential function is. So a linear function is equal differences over equal intervals, right? Equal differences over equal intervals. That means that if I take my y values and I subtract them from each other, from one term to the next, I'll get the same difference each time. Whereas equal factors over equal intervals, equal factors over equal intervals is what represents an exponential. And that means that if I subtract them, I'm not going to get the same number. What I have to do is I have to divide them, or I have to look and see what number, what factor am I multiplying one term by to get to the next one. So they're equal factors. So that's involving multiplication. All right? Now, let's take a look at my graph, my little table here, a linear and exponential compare and contrast. So let's go ahead and fill this in. The first thing is when you're looking at a linear equation, I'm going to show you two different equations. One is one that we're very familiar with, y equals mx. I'm going to actually write ax. Don't let that freak you out. Plus b. The a just is the same as the m. Both the a and the b are constants, okay? And we also have a recursive function that says something like this. F of 1 equals a1, okay? And f of, that means the first term, n equals f of n minus 1 plus d, the difference, okay? Our exponential equation looks like this. Y equals a times b to the x power. It's a little bit different than what I showed you in the last video, mainly because oftentimes our a is our starting term, it's where we're starting, and b is our common ratio that is going to be put to the power of all of the different x's, okay? And then we've got our recursive looks something like this. F of 1 equals a1 and f of n equals f of n minus 1 times the constant ratio. All right? All right? So that is some of our equations. Now, the rate of change in a linear equation, we call it a, we actually call it a constant rate of change, don't we? I'm going to write constant up here. And for an exponential, we call it a constant factor of change or change factor. If we want to graph a linear equation or a linear function, it would look something like this. This is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So if we wanted to graph something, it might look, we might have a point here, and a point here, and a point here, and then we would graph, see if I can do this, a line connecting the two. Okay? But on an exponential function, let's have our equal intervals be 1, 2, 3, 4, 5, 6. And I'm going to actually make this be 10, 20. We're going to make our intervals be a little bit different. They're still equal, but we're going to say when we'll say 1, what do I want to do? Let's see. Let me think about this. Okay, let's just assume that our function looks something like this. We'll do x and y, 1, 2, 3, 4, and we'll say that y equals 3 to the x power. So that when x is 1, y is 3. When x is 2, y is 9. When x is 3, y is 27 and 81. And we won't even get that far. So we're going to say when x is 1, y is 3, which is right about there. When x is 2, y is 9, which is right about there. When x is 3, y is 27, which is right about there. And then, of course, the 81 would be way up here, right? 50, 60, 70, 80 would be way up here. I'll even make a little point there so you can see it. And then let's actually change the color. And we've got okay, so that's an exponential graph. So you can see the difference, right? All right, the growth pattern is for a linear equation is steadily, it's a steady rate. Steady, okay? But for exponential, it's rapidly growing. Rapid growth. An example of a linear equation or a linear function, x, and we'll say f of x, might be this, 1, 2, 3, 4. Let's say 2, 5, 8, 11. The table shows a rate of change, add 3, right? So when you look at the differences, it's add 3. A table for an exponential function would look like this. We could use the same one we were doing over here, 3, 9, 27, 81. And this time, we're multiplying by 3. We're not adding 3, we're multiplying by 3. Constant factor, okay? So an example A written example of a linear equation would look like this. Charles had $3 in his bank account and earned $2 per week as an allowance, and we would write it like this. Y, meaning the amount he has in his bank account, equals how much is he putting in each week? $2. X is the number of weeks, plus the amount that he started with, $3. Do you see how that translates to a linear equation? But this one, there were 3 goldfish in the tank, and the population doubled every month. The population doubled every month. So that would mean that I started with 3, okay? I started with 3 goldfish, and I'm going to multiply that times 2 every single month, and the month is the x. So 3 times 2 to the x power. Let me show you how that looks on a table. That was an x. So on the first month, he had 3. Actually, we could even start on the 0 month. When he first started, he had 3. Okay, 2 to the 0 power is 1. 3 times 1 is 3. Okay, after the first month, he had 3 times 2 to the 1 power. So 2 to the 1 power is 2. 3 times 2 is 6. On the second month, he had 3 times 2 to the second power. Well, that's just 2 times 2, which is 4. 3 times 4 is 12. Do you see how it's doubling every time we multiply by 2? That's what those powers are. Okay? And then, of course, this one, you can say that on week 0, when he just started, he had 3. And after the first week, he had 2 times 1 is 2 plus 3 is 5. And on the second week, he had 4 plus 3 is 7. So that's how it shows up in a table. So that's just a really quick review, and you need to be very familiar with this because you need to be able to look at examples and be able to tell whether it's something as a linear function, whether it's an exponential function, or if it isn't either, because there are other types of functions that we haven't learned yet. We've just been focusing on linear and exponential. So let's go ahead and get started by looking at some examples. Decide if it's a linear, an exponential function, or neither, and explain why. Look at this first one, y equals 7x. Is it linear, exponential, or neither? And explain why. All right, well, hopefully you said that it was linear. And the way that I would know that this is linear is I see this as a linear function or a linear equation. All I have to do is add 0, and that looks just like y equals mx plus b. Y equals mx plus b with a slope of 7. That's my rate of change. It's linear. You could also have set up a table and seen that when x is 1, y is 7. When x is 2, y is 14. When x is 3, y is 21. And each time I increased by 7, a constant rate of change. Okay, let's look at the next one. Tennis tournament. Take a look at that one. You can see that there are rounds and there's a number of players left. So in the first round, there are 64 players left. In the second round, there are 32 players left. In the third round, there are 16 players left. In the fourth round, there are 8 players left. In the fifth round, there are 4 players left. So at the end of 5 rounds, there are 4 players left. So is this a linear, an exponential, or neither? Well, hopefully you noticed that for Fred to get from 64 to 32, I had to multiply by 1/2. To get from 32 to 16, I had to multiply by 1/2. There is a constant factor of change, or a change factor. I'm multiplying by 1/2. So that means this is exponential. You could have also, if you wanted to, you could have graphed this. And if you graphed it on a piece of graph paper, you would have seen that there was a rapid decline. You'd started with 1 being 64, 2 comes down to 32, 3 comes down to 16, 4 comes down to 18. You can see right away that that is a rapid decline. You might have also said, well, this looks like a geometric sequence to me, and a geometric sequence is an exponential function. Lots of ways to tell that this is exponential. Look at the next one. The function is decreasing at a constant rate. What is this? Is this linear, exponential, or neither? Hopefully, you saw this word right here, constant rate, and you said, constant rate. That means it's a linear function, linear. Next one, negative 3x equals 4y plus 7. Negative 3x equals 4y plus 7. Is this linear, exponential, or neither? Just because an equation is written in a different form does not mean that it isn't a linear equation or isn't an exponential function. This one is linear, and the way I know that is I could actually subtract 3 or add 3x to both sides, or I could subtract 7. Actually, I probably would subtract 7 from both sides, and I get 4y equals negative 3x minus 7, divide by 4, and I get y equals negative 3/4 x minus 7. And that's a linear equation. It's linear. You could have also just rearranged it and subtracted the 4y, or added the 3x and subtracted the 7 and had 3x minus 4y equals negative 7. That's a linear equation also in standard form. So any of those would have worked for you. It's a linear equation. I also could have graphed it. I could have tried graphing it. I could have tried doing a table, and I would have seen that there's a constant rate of change. So this one is linear. Let's look at this one. Y equals 7x squared. Tell me if that is linear or if it is exponential or if it is neither. This one may have tricked you up because you might have seen that exponent and said, oh, it has an exponent, therefore it must be exponential. But I will tell you that it's neither. It is actually a quadratic, which we have not talked about yet. Remember that an exponential function has the variable as the exponent. Look up here. The variable is the exponent. The variable isn't the base, the variable is actually the exponent. So this is neither. If it had said 7 to the x power, then it would have been exponential. If it had said this, 7 to the x power. Well, you can't even read that, but you get the idea. Okay? Look at the next one. F of 1 equals 7. F of n equals f of n minus 1, the previous term, minus 4. Is that linear, exponential, or neither? Well, right away, you should have seen that this is a recursive formula. So you say, I start at the 7th, my first term is 7, and to get the next term, I have to take the previous term, so I can start at 7. So if to get the second term, I have to look at the first term, which is 7, and subtract 4. And each time I'm subtracting 4, this right here is my constant rate of change. Therefore, this is linear. Next one. Thinking about height in inches, somebody's height in inches. Compare that to their shoe size. If somebody is 62 inches, then their shoe size is 6. If somebody is 74 inches, then their shoe size is 13. If somebody is 70 inches, their shoe size is 9. If someone is 67 inches, their shoe size is 11. 53 inches, their shoe size is 4. 58 inches, their shoe size is 7. Is this linear, exponential, or neither? Well, it is neither. You could have rearranged these, made them in order, put the 53 first, and then get to the 58. And you could look at the change factor is 4, right? Or 3. And then you could go to the next one, and you can see that it's pretty random. Someone who's 62 inches, it definitely increases, but look at how it increases from 67 to 74. It's 13. You could have plotted it on a graph, you could have graphed it, and you would have seen a steady increase. Typically, someone's height in inches does predict closely their shoe size, but there's not an exact representation. So it's not going to be a steady increase in that there's a constant rate. There's a steady increase, but there's not a constant rate. So this is neither. Last one. Each point on a graph is exactly 1/3 of the previous point. Is it linear? Is it exponential? Is it neither? This time, you should have said that this was exponential. And the way that we know that is we think about what it's saying. Each point on a graph is exactly 1/3 of the previous point. So if the first point was, let's see, let's do it like this. We can create a table, X and Y. If the first point was 9, then the next point would be 3, right? And then the third point would be 1, and the fourth point would be 1/3. So you can see that it's decreasing by 1/3. We're multiplying it by 1/3, so it's exponential. There's a change factor. All right, you could graph it. You could actually graph this, and you would see that it would look something like this, coming down. Okay, well, that is our lesson for today. Comparing and contrasting linear and exponential functions. Make sure that you write a key idea. Think about what it is that makes a linear equation different from an exponential function, and how is it that you can tell the difference between them. You'll want to be able to do that because you're going to be doing a lot of that in the coming days. And once you've written that down, I'll see you in class.